Okay folks, so today we're going to do a optimization routine called grid search, step search, however you want to call it. I did not prepare for this video at all. I'm going to go on the fly and we're going to see what happens. So here we go, function, step search. I did not prepare for this because frankly I want you to see my thought process for everything. Okay, so in order to search for something, to optimize something, we need a function itself. So let's do a really easy one. Y equals f of x, y equals x dot half squared minus 1. Okay, the optimum location, x opt is 0 and y opt is -1. Okay, very, very simple. First thing I probably want to do is I want to just plot it. So let's go -1 to 1. Y equals f of x, plot x comma y. Let's throw a clear CLC and a close all. I can throw a clear in the function because there are no inputs and outputs. I'm going to run this. There's my function. Very cool. Okay, so let's kick off this step search. So step search is a loop, and so you need to know what x actual is, or let's just do max iterations, or step size actually. So let's initialize my step size equal to say 0.5. Let's make my initial x, let's make it -1, and basically you just you kick off your loop while step size is greater than what do you want your step size to be? 0.01? 001? Let's say 01. Okay. Alright, so we now have this loop where we're just iterating, but we need to move our x and we need to check our step size. Okay. So doing a one-dimensional step search, you need to compute left x, which is f of x0 minus del x. In this case, it's not a del x, it's step size. Okay. Then we need to check the right x, which is f of x0 plus step size. And then essentially we need to say if left x is less than f of x0, then x0 equals... Well, actually, you need to check which one is the smallest. So let's make a vector. So vectors. How about x f samples? Let's do that. Let's make it the vector left x, x0, or f of x0, and right x. And let's call this f left of x, f right x. So that's because it's really the function. And then what we want to do is we want to say, okay, give me the minimum of all of these points. So say f min equals, is f min a function? Let's check. F min is not a function, perfect. F min is minimum of f samples. And then the location is I'm going to find where f min is equal to f samples, and that means that x new, the new coordinate, is equal to so I need x samples here. So let's do it this way. Let's say x samples is x0 minus step size. Let's say x0 plus step size. Okay, and then I'm going to say f samples is actually just f of x samples. That makes that easier, so then I can get rid of these lines of code. So let me comment this. So these are my 3 sample points I'd like to check. This is the function evaluated at my sample points. This is the minimum of the 3. This is the vector location of my minimum. And then I'm going to use this to give me x0, which is essentially my x sample points of location. So this is a Boolean. This is a number between 1 and 3. And so when I grab this, I'm grabbing the x that computes f min, which equals f of x. Okay, let's see, why doesn't it like this? Removing the call to find and using logical indexing is usually faster. Okay, I'm going to let you fix it. Let's see what happens. Yeah, that sounds good. Okay, forget the find function. So basically, what I did was I said, okay, take this vector of f samples, compute where it's equal to f min, and that's going to give me a vector. So it's not going to be a number between 0 and 1. This is a vector of zeros and ones, and then this is just going to grab the x that is equal to that. Okay, so if I'm going to get rid of this guy, okay, and I'm going to put this over here and put this over here, and I'm just going to hit go, and what we'll find is it's very quick. I mean, this code is super fast. What we can do to see this better is we can throw a hold on here, and then I'm going to throw a plot. I'm going to throw a x0, f of x0. I'm going to throw a red star here with a marker size of 10, and I'm going to throw a draw now. I'm going to pause. I'm going to pause it for 0.01 seconds. Let's see if we can see that. No, that was too fast. Oh, so our step size is really big. Let's start our step size out like that so we can see some jazziness. Okay, so that's still too fast. Let's pause it for 0.5 seconds. Okay, so here we are stepping through, and then once we get to here, you know, we're done because the guys to my left and right are just as big. Let's make our step size not so uniform. Let's actually just shift this 0. Actually, let's just shift it by e because we can. Oh, e is not a function. Exp of 1. Okay, cool. All right, so now it's something weird. So there's no way it'll actually be right at there. Oh no, the minimum is actually still there. Oh, okay. So this is what we need to do. We need to do x minus exp of 1. There we go. Ha! I like that. Minus 1. So x opt is now e, which is like 2.718. So my bounds aren't big enough. So let's make it minus 3 to 3. Okay, here we go. So now we're stepping through, and so my minimum is somewhere over here. Let's go minus 5 to 5 so we can see it, and then let's make our pause not so big. I'm hitting Control C to kill this code. All right, there we go. So there's my step search kind of marching along, and then stops here. But see, 2.7 isn't really that high of a threshold. So basically, somewhere around here, you're going to find that this x0 and this x0 is actually the minimum. So what you want to do is you want to say if lock of 2 is equal to 1, which essentially means that the minimum is the point you are sampling. Then what you want to do is you want to have your step size. So step size equals step size over 2 and end. Okay, so here we go. So that should work. So we're marching along. We're going to have our step size. Boom. So look at that. Did you notice that right here we went 2.7, 2.7, 2.7, but then we halved our step size and we kept going. So if I make my tolerance even smaller, like super ridiculously small, we'll march along. No big deal. And then now we're really talking about getting converged to E here. If we make our step size bigger, now we can do that. You can kind of see your step size sort of, jump around. And if we come in here, you can start seeing some cool stuff. What I'd actually like to see, what I think would be cool is if we did colors here. And so I'm going to do red, green, black, magenta, yellow, cyan. Do I have blue in here? Okay. And then I'm going to set IDX equal to 1. And then I'm actually going to plot, instead of in red star, I'm going to do tick mark, comma, tick mark, end bracket. I'm going to do colors of IDX. But when I have my step size, I'm going to do IDX equals IDX plus 1. And so what that's going to do is it should change colors. Yeah, do you see that? That was like a crazy light show there. So I'm going to maximize this. So basically we're marching along, and then all of a sudden we're having our step size, and so the colors are changing. So I'm going to do that one more time, maximize the screen. So we're coming in here, changing our step size, colors are changing. It's like a MATLAB rave over here. So that was super fast. There's a million ways to do this. This is probably not the most elegant way to do it, but basically it gets us to our answer. So let's compute our absolute error, and that's just going to be absolute of x0 minus exp of 1. And so if we run this, let's get rid of that pause, and let's throw a draw now in here. And oh yeah, that's right. So if idx is greater than length of colors, idx equals 1, and that way you won't get this error, index exceeds matrix dimensions. So if we run this, that should be really fast. And look at our error, 4 times 10 to the minus 6. If we make our step size just go to 0.01, our error is now minus 4. If we say go to 0.1, our error is 0.03. You know, if we go to say 0.25, our error should be quite large. But you know, basically, you're stepping through and you're computing your answer here. We can compute iterations. Iters equals 1. Iters, let's do 0. Iters equals iters plus 1. And we can output absolute error and iters. And so there we go. We got 24 iterations like this. But if we just do 0.1, we've got 11 iterations. So you can kind of see that number of iterations. What else might you want to do? Maybe you want to plot xvec as a function of time, or a function of iteration number. So you could say in here on line 30, just say maybe xvec of maybe iters. Yeah, you could do that. So make this x0, and then you could say iters equals x naught. And actually, I think if you do that, you need to do this up here. And then we can drop a figure down here, and we can plot x, what was it? What did I call it? X iters? Or xvec? Let's call it x samples. I'm trying to make my variable names like more descriptive. X samples. And so iters is fine there. So then we want to do x samples like that and plot that, and there we go. So there is the function as we go, number of iterations. I only have 3 here. That seems weird. Why? Oh, because x samples is done twice. Oh, that's annoying. Okay, well, okay, so these aren't samples. So I'm just going to call this x iters. Another interesting bug. This is what happens when you just code on the fly. Okay, boom. All right, there we go. That's what I'm talking about. So, you know, basically it's like marching along like this, stays the same, have our step size, stays the same. And so if we make it like, you know, stupid small, and we run it again, you know, now we're talking like, you know, boom, boom, boom. Oh, and it looks like it actually like goes the other way at one point. That's probably some numerical precision. This looks like some sweet second order response here. But yeah, anyway, I mean, we converged -07, 35 iterations. It's brute force, but it works pretty well. All right, I'm rambling. Good luck, you guys. Oh, I guess I should probably show you the code. So here's function step search, clear CLC, close all. Plot the function, initialize our step size, initialize our initial conditions, fancy color plotting, fancy color indexing, saving your iterations, saving your x values of your iterations while your step size is greater than this, stepping your iterations, saving your conditions. These are my sample points, so where I am, to the left, to the right. That's like a song, right? And then the function evaluated at those sample points, compute the minimum of those 3, figure out which one is the minimum in the location, and then grab that x coordinate from here. And then if the location of 2 is 1, that means that basically x0 didn't change. So this x0 is the same as this x0. You have your step size. And then this is a color thing, so don't worry about this. And then I plot it and I draw now, so I can watch it. I compute my absolute error. Here's my iters. I drop a figure down and do another plot. And then here's my function here that I optimized. And there you go. Pretty cool stuff. Here's my 2 plots. See if you guys get the same thing. Good luck.